Imagine standing at the bow of a vessel unlike any other. Not a ship that cuts through ocean waves, but one designed to sail through the darkness between stars. Your course is set straight ahead, never turning, never stopping. Picture yourself at the controls, watching as the familiar blue marble of Earth shrinks to a pale dot, then vanishes completely. The sun becomes just another star, and then it too fades into the cosmic tapestry behind you. You are alone now. The vessel hums quietly as it pushes forward into the unknown. There is no destination programmed into your navigation system. There is only forward, forever. What happens when you travel in one direction through space and never stop? It sounds like a simple question, perhaps even a child's curiosity. But contained within it are some of the most profound mysteries of our universe. Would you eventually reach the edge of everything? Would you find yourself returning to where you started, like circumnavigating a cosmic globe? Or would you discover something else entirely, something our minds cannot yet comprehend? The deeper we examine this question, the more it reveals about the fundamental nature of reality itself. It challenges our understanding of infinity, of beginnings and endings, of the very fabric of space-time. Tonight, we will embark on this journey together. We will follow the trail of human curiosity that has led us from ancient cosmologies to the cutting edge of modern physics. We will explore what happens when we keep going, always forward, never stopping. This is not merely a thought experiment. It is an expedition to the furthest reaches of scientific understanding, to the boundary where knowledge fades into mystery. The question of endless travel through space forces us to confront the most basic assumptions about our universe. Is it finite or infinite? Does it have an edge, a boundary, a limit? Or does it continue endlessly in all directions? For thousands of years, these questions remained in the realm of philosophy and speculation. But today, we have tools and observations that bring us closer to answers than ever before. Telescopes peer across billions of light years. Sophisticated mathematical models simulate the behavior of space-time itself. Particle accelerators probe the fundamental forces that shape existence. And yet the ultimate nature of our cosmic home remains elusive. The universe guards its deepest secrets carefully, revealing them only to those patient enough to observe and curious enough to question. As we drift through the night together, I invite you to release your earthbound perspective. Let your mind expand beyond the familiar horizons of our planet, beyond the solar system, beyond even the galaxy we call home. The journey we are about to undertake has no actual physical destination. Instead, it leads inward to a deeper understanding of the cosmos and our place within it. Think about what it truly means to keep traveling forever. The word forever itself challenges our human sense of time and mortality. We live in a world of beginnings and endings, of borders and boundaries. But the universe operates on scales that dwarf our experience. Distances measured not in miles or kilometers, but in light years. The staggering distance that light itself, the fastest thing we know, travels in an entire year. Time stretched not across days or years, but across billions of rotations of our planet around its star. Space expanded not across cities or continents, but across clusters of galaxies, each containing hundreds of billions of stars. In this vastness, our question takes on new dimensions. When we ask what happens if we keep traveling through space forever, we are really asking about the nature of infinity itself. Is infinity merely a mathematical concept, or is it a physical reality? Can something truly have no end, no boundary, no limit? Our intuition rebels against such notions, yet mathematics embraces them. The ancient Greeks grappled with this paradox. Zeno famously argued that motion itself was impossible because to travel any distance, you must first travel half that distance, and before that, half of that half, creating an infinite series. Yet we move through space every day. Something in our understanding must bridge the gap between the finite and the infinite. between what we can comprehend and what exists beyond our mental grasp. Tonight, we will navigate these philosophical waters alongside the physical journey through space. We will see how the question of endless travel reveals the tension between our human need for closure and the universe's apparent indifference to our cognitive limitations. As your consciousness drifts with these words, remember that you are already traveling through space. The Earth rotates, orbits the Sun, which orbits the galactic center, which moves through the cosmos. We are all cosmic travelers, whether we recognize it or not. The only difference in our thought experiment is that we choose a single direction and never deviate from it. So settle in as we prepare to venture farther than any human has gone before, not in body, but in mind. The journey ahead will take us to the very limits of scientific understanding and beyond. Tonight, we explore what happens if you keep traveling through space forever, and why the answer tells us more about the nature of reality than almost any other question we could ask. Chapter 2. The Human Compass. Why Infinity Matters. Why does this question of endless travel captivate us so deeply? Perhaps because it speaks to something fundamental in the human experience, a relentless drive to explore, to push beyond known boundaries, to seek what lies beyond the horizon. Throughout history, explorers have ventured into uncharted territories, sailors have navigated vast oceans, and mountain climbers have ascended treacherous peaks. The urge to discover what lies beyond is embedded in our DNA. Space represents the ultimate frontier, the final unexplored realm that stretches beyond anything we can physically reach in a human lifetime. It is both a literal and metaphorical horizon that recedes as we approach it. When we contemplate endless travel through the cosmos, we are continuing this ancient tradition of exploration, but on scales that transcend our physical limitations. We explore with our minds what our bodies cannot reach. There is comfort in this mental journey, despite its vastness. The universe may be incomprehensibly large, but it follows patterns we can recognize and laws we can understand. Even in infinity, there is order. This brings us to a profound realization. Our question about endless travel isn't just about what lies out there. It's about finding our place within the cosmic framework, about orienting ourselves in relation to everything else that exists. Human beings have always used the stars to navigate. Ancient sailors followed celestial patterns to cross oceans. Desert travelers oriented themselves by the night sky. The cosmos has been our guide for millennia. Now, as we peer deeper into space than ever before, we find ourselves engaged in a different kind of navigation, not across physical distance, but through layers of meaning and existence. The question of what happens if we travel forever forces us to confront our cosmic insignificance while simultaneously celebrating our cognitive significance. We may be tiny, but we can comprehend the vast. There is something profoundly reassuring about this paradox. We exist as conscious beings in a universe large enough to make us statistically irrelevant, yet complex enough to produce minds that can contemplate its entirety. This perspective shifts our relationship with existential concerns. When viewed against the backdrop of cosmic scales, many of our daily worries diminish in importance. The universe continues regardless of our individual struggles. Yet rather than inducing despair, this cosmic perspective often brings peace. There is liberation in recognizing our small place in an immense reality. We are freed from the burden of cosmic significance. At the same time, our ability to comprehend the vastness around us grants us a unique position. We are the universe becoming conscious of itself, matter organized in such a way that it can contemplate its own existence. This recursive awareness creates a profound connection between ourselves and the cosmos. We are not separate from the universe. We are an intrinsic part of it, as integral as stars or galaxies. The atoms in our bodies were forged in stellar furnaces billions of years ago. The carbon, oxygen, and nitrogen that form our tissues traveled unimaginable distances before becoming part of us. In a very real sense, we are already travelers through space and time. Our component parts have journeyed across the cosmos for billions of years to create the temporary arrangement we call a human being. When we ask what happens if we keep traveling through space forever, we are really asking about our cosmic context. We seek to understand the arena in which our brief existence plays out. This context matters because it shapes how we perceive our lives. A universe with an edge creates different meaning than an infinite one. A bounded cosmos suggests limits. An unbounded one suggests possibility. Some find the prospect of endless space unsettling. Without boundaries or limits, we can feel adrift, anchorless in a sea too vast to comprehend. We evolved to understand defined spaces with clear parameters. Others find profound comfort in cosmic infinitude. An endless universe means endless possibility, endless variation, endless opportunity for existence in all its forms. Nothing is truly lost in infinity. It merely changes form. This duality reflects our complex relationship with the unknown. We simultaneously fear and are drawn to it. We want answers, yet we are invigorated by questions that lead to further questions. The practical impossibility of the journey we're contemplating, traveling forever through space, does nothing to diminish its philosophical importance. Some questions matter precisely because they cannot be answered through direct experience. Instead, they serve as conceptual frameworks that help us organize our understanding of reality. They are mental models that give structure to our cosmic imagination. As we contemplate traveling forever through the void, we inevitably confront questions about endings and beginnings. Does the universe have a boundary? Did it have an origin? Will it have an end? These questions echo our awareness of our own mortality. We know our individual journeys have definite beginnings and endings. We struggle to apply this pattern to the cosmos itself. Yet applying human timeframes to the universe creates a category error. The cosmos operates on scales that make our lives seem instantaneous by comparison. What appears eternal to us may be merely a phase in cosmic evolution. This mismatch between human and cosmic timescales creates a perceptual challenge. We struggle to truly internalize just how vast space is, just how long cosmic processes take, just how small we are in comparison. But rather than diminishing us, this vastness elevates the miracle of our existence. Against all odds, in this incomprehensibly large universe, here we are, contemplating it all, asking these profound questions. As we continue our journey tonight, keep this perspective in mind. We may be small, but our capacity for wonder makes us significant participants in the cosmic drama. We matter because we can ask why anything matters. The universe, in all its immensity, has produced beings capable of contemplating infinite journeys through space. That alone gives our question meaning beyond mere curiosity. It connects us to the fundamental nature of reality itself. So as we drift together through this thought experiment, remember that we are not just passive observers of cosmic vastness. We are active participants in the universe's ongoing journey toward greater complexity and awareness. Chapter 3. The First Wayfarers' Origins of Our Cosmic Quest. Humanity's fascination with the infinite journey begins with our earliest ancestors. Imagine the first humans gazing upward at the night sky, untouched by light pollution. The full glory of the cosmos spread above them like a luminous ocean. They had no telescopes, no physics equations, no space probes. Yet they still wondered what lay beyond the visible stars, beyond the edge of their perception. This questioning is as old as consciousness itself. Ancient civilizations across the globe developed cosmologies to explain the apparent motion of celestial bodies. These were our first attempts to comprehend the architecture of space and our place within it. In Mesopotamia, around 3000 BCE, the Sumerians envisioned the universe as a series of flat disks. The Earth floated on an infinite ocean, while the sky formed a dome overhead, studded with stars. The ancient Egyptians saw the sky as the goddess Nut, her body arching over the earth. Each night, the sun god Rio would travel through her body, emerging reborn each morning in the east. These early models reveal something important about human cognition. We instinctively seek boundaries, edges, and defined structures. The concept of truly endless space challenges our evolved mental frameworks. The ancient Greeks brought more geometric precision to cosmology. Around 500 BCE, Pythagoras proposed that Earth was spherical, not flat. This was a revolutionary concept that transformed how we understood our place in space. A century later, Aristotle developed a comprehensive model of the universe with Earth at its center, surrounded by concentric crystalline spheres carrying the planets, sun, and stars in their eternal rotations. This geocentric model prevailed for nearly 2,000 years. It presented a bounded universe with Earth at its center and the sphere of fixed stars as its outer boundary. Space had an edge, but even then, philosophical minds questioned this limitation. The pre-Socratic philosopher Archytas posed a thought experiment. If I arrived at the outermost edge of the heaven, could I extend my hand or staff beyond it? This simple question contains the seed of our journey tonight. If space has an edge, what lies beyond it? If someone travels to this boundary, what happens when they try to cross it? The intuitive impossibility of a spatial boundary troubled many ancient thinkers. Lucretius, the Roman philosopher, argued that if there were an edge to the universe, one could throw a spear at it. And if the spear were stopped, then something must exist beyond the supposed edge to stop it. But if the spear continued, then the edge was not an edge at all. Space must continue. This argument, simple yet profound, points to the logical problems with a finite universe. Our intuitions rebel against the concept of absolute boundaries in space. There must always be an other side. As humanity's understanding evolved, our cosmic models grew more sophisticated. In the 16th century, Copernicus placed the sun, not Earth, at the center of the universe, beginning a profound repositioning of humanity. No longer at the center of creation, we became residents of just one planet among several, orbiting an ordinary star. This conceptual demotion continued as our instruments revealed ever greater cosmic scales. Galileo's telescope showed that the Milky Way consisted of countless individual stars. The universe was far larger and more populated than anyone had imagined. The journey through space would be longer than we thought. By the 18th century, philosopher Immanuel Kant proposed that some nebulous objects might be island universes, entire galaxies, separate from our Milky Way. The scale of space expanded exponentially in our understanding. Kant also wrestled with the philosophical implications of infinite space. He recognized it as an antinomy, a logical contradiction where both a thesis and its antithesis appear equally reasonable. On one hand, a bounded universe creates the problem of what lies beyond. On the other, an infinite universe creates conceptual problems about completed infinities. Both possibilities challenge human reason. Throughout this period, the actual physical nature of space remained mysterious. Was it an empty void, as Democritus had suggested in ancient Greece? Or was it filled with an invisible medium? Newton's laws of motion and gravity described how objects moved through space, but said little about space itself. It appeared as an absolute, unchanging background against which cosmic drama played out. This view persisted until the early 20th century, when a patent clerk in Switzerland published papers that would revolutionize our understanding of the cosmos. Albert Einstein transformed how we conceive of space itself. Einstein's special relativity, published in 1905, showed that space and time were not separate and absolute, but interconnected and relative. The consequences were profound for our imaginary journey through space. For one, there is no universal now across the cosmos. Time passes differently depending on relative motion and gravitational influence. A traveler journeying forever through space would experience time differently than those left behind. 10 years later, Einstein's general relativity revealed that space itself isn't just a fixed backdrop. It's a dynamic fabric that can curve, stretch, and warp in response to matter and energy. This reconception changed the nature of our question. When asking what happens if you travel forever through space, we must now consider that space itself has properties that affect the journey. The path of a traveler moving in what seems like a straight line might actually be curved by the invisible architecture of spacetime. The shape of space itself would determine the fate of our endless journey. As the 20th century progressed, observations continued to expand our cosmic horizons. Astronomer Edwin Hubble proved that nebulae were indeed separate galaxies, vastly increasing the known size of the universe. Hubble also discovered something unexpected. These galaxies were moving away from each other. The universe wasn't static, it was expanding. This observation would lead to one of the most revolutionary concepts in cosmology. If galaxies are moving apart, then rewinding cosmic history would bring them closer together. Following this logic to its conclusion, suggested that the entire universe originated from an incredibly dense, hot state. This idea developed into what we now call the Big Bang Theory. It proposed that space itself has been expanding for approximately 13.8 billion years, carrying galaxies along like raisins in rising bread dough. This new understanding transformed our original question. If space itself is expanding, what does it mean to travel forever in one direction? Are we moving through space, or is space itself in motion? Throughout the mid-20th century, competing models tried to explain the universe's large-scale structure. The steady-state theory proposed continuous creation of matter as space expanded, maintaining a constant density throughout eternity. This model avoided a beginning to the universe, which many scientists found philosophically troubling. If the universe had a beginning, what came before? What caused it? These questions seem to lead outside science itself. But observational evidence continued to favor the Big Bang model. In 1964, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation, the afterglow of the Big Bang itself. This observation, along with others that followed, established the Big Bang Theory as the standard model of cosmology. Our understanding of what it means to travel through space forever had to incorporate this expanding framework. Chapter 4: Measuring the Immeasurable, the Scale of Our Journey. To truly comprehend what would happen on an endless journey through space, we must first understand the scale of the cosmic terrain we would traverse. Our human minds struggle to grasp astronomical distances. Let's begin close to home. Light, the fastest entity in the universe, travels 186,282 miles per second. At this incredible speed, light takes only 1.3 seconds to reach the moon from Earth. To reach Mars, our closest planetary neighbor beyond the moon, light requires between 3 and 22 minutes, depending on the orbits of both planets. Already, we're dealing with distances that challenge human intuition. Voyager 1, humanity's most distant spacecraft, has been traveling since 1977. After more than 4 decades of continuous flight at speeds reaching 38,000 miles per hour, it has only just left our solar system. Even at these impressive velocities, Voyager would need over 70,000 years to reach Proxima Centauri, the nearest star beyond our Sun. This gives us a humbling perspective on interstellar distances. Let's scale up our imaginary vessel to something faster, perhaps a ship traveling at 1/10 the speed of light. Even at this incredible velocity, the journey to Proxima Centauri would take over 4 years. Our Milky Way galaxy contains between 100 and 400 billion stars, spread across a disk roughly 100,000 light-years in diameter. At 1/10 light speed, crossing our galaxy would take about 1,000,000 years. But the Milky Way is just one galaxy among billions. The nearest major galaxy to ours, Andromeda, lies approximately 2.5 million light-years away. The light we see from it today began its journey when early humans were first appearing on Earth. Our local group of galaxies, which includes the Milky Way, Andromeda, and about 54 smaller galaxies, spans roughly 10 million light-years. Beyond that lies the Virgo supercluster, a vast collection of galaxy groups and clusters. Recent astronomical studies reveal that the Virgo supercluster is itself part of an even larger structure called Laniakea, spanning more than 500 million light-years. These nested structures continue to grow in scale as we zoom out. The observable universe, the portion we can theoretically see, extends approximately 93 billion light-years in diameter. This seemingly contradicts the universe's age of 13.8 billion years, which requires explanation. The discrepancy arises because space itself has been expanding throughout cosmic history. The most distant objects we can observe have been carried much farther away since their light began traveling toward us. This brings us to a critical point in our journey. The expansion of space affects what would happen if we traveled forever in one direction. The universe is not static. It's dynamically changing as we move through it. Observations show that this expansion is accelerating, driven by a mysterious force scientists call dark energy. This acceleration has profound implications for our hypothetical endless journey through space. As we travel outward, the space ahead of us continues to stretch. Distant galaxies move away faster than closer ones, creating a cosmic horizon beyond which objects recede faster than the speed of light. This doesn't violate Einstein's speed limit because the galaxies aren't moving through space at these speeds. Rather, the space between them is expanding. It's like drawing dots on a balloon and then inflating it. If our imaginary vessel could somehow maintain a straight-line course forever, we would eventually approach this cosmic horizon. Beyond it lie regions of space that we can never reach, no matter how long we travel. This creates an interesting paradox. In an infinite, expanding universe, there are still places permanently beyond our reach. The journey could continue forever without accessing the entire cosmos. Let's consider another possibility. What if the universe isn't infinite, but has some complex geometric structure? Einstein's general relativity tells us that space can curve in response to mass and energy. If the universe contains enough matter, this curvature could bend space back on itself, creating what mathematicians call a closed geometry. In this scenario, traveling forever in one direction might eventually bring you back to your starting point. Imagine the surface of a sphere. An ant walking in what it perceives as a straight line will eventually circle the globe and return to its starting point. A closed universe would operate similarly, but in 3 dimensions. Current observations, however, suggest that our universe is remarkably flat in its large-scale geometry. Measurements of the cosmic microwave background radiation indicate that parallel lines would remain parallel even over vast distances. This flatness, combined with accelerating expansion, supports the model of an open universe that will continue expanding forever. In such a cosmos, our endless journey would never return us to our starting point. But the nature of space becomes even more complex when we consider quantum mechanics. At the smallest scales, space may not be continuous but quantized, composed of indivisible units like pixels in a digital image. Theories of quantum gravity, which attempt to reconcile general relativity with quantum mechanics, suggest that space itself might emerge from more fundamental phenomena. The smooth journey we imagine might be an illusion. At the boundary of current physics lies the multiverse hypothesis, the idea that our universe might be one of many, perhaps infinite, universes existing simultaneously. Our journey might cross into entirely different realities. These theoretical frontiers remain speculative, but they highlight how our understanding of endless travel through space depends on the underlying nature of reality itself, questions at the cutting edge of physics. As we contemplate these vast scales, we must acknowledge the practical limitations of any real journey. Even if we could travel at the speed of light, which physics prohibits for objects with mass, much of the universe would remain forever beyond our reach. The light from galaxies at the edge of the observable universe has traveled for almost the entire age of the cosmos to reach us. By the time we could travel there, those galaxies would have moved much farther away. This creates a fundamental asymmetry between what we can observe and what we can visit. We can see much more of the universe than we could ever physically reach, even given infinite time. This limitation is not merely technological, but woven into the fabric of physics itself. The expanding universe, combined with the speed limit imposed by relativity, creates boundaries that no traveler can cross. And yet, there's something profoundly moving about this cosmic perspective. It reminds us that exploration isn't always about reaching a destination. Sometimes it's about the journey itself, about pushing boundaries, even when we know they cannot all be crossed. As we approach the end of this first segment of our journey, we stand at a threshold. We've examined the scales involved in cosmic travel and glimpsed the fundamental limits physics places on our hypothetical endless voyage. But we have only begun to explore the implications. What would such a traveler experience? How would time dilation affect their perception? What strange objects and phenomena would they encounter in the deepest reaches of space? And perhaps most intriguingly, what is our inability to travel to the edges of the observable universe tell us about the nature of knowledge itself? Are there fundamental limits to what we can know, just as there are limits to where we can go? In the next segment of our journey, we will venture into these deeper waters. We will explore the strange objects that populate the cosmic ocean, neutron stars, black holes, and perhaps stranger things yet undiscovered. We will examine how the laws of physics themselves might change under extreme conditions, altering the very nature of our endless voyage. And we will confront the philosophical implications of a journey without end. So stay with us as we continue to unravel one of the most profound questions we can ask. What really happens if you keep traveling through space forever? The answer may change how you see not just the cosmos, but reality itself. Chapter 5: Cosmic Contradictions When Models Collide. As we continue our endless journey through space, we encounter a peculiar problem. The further we travel from Earth, the more our observations seem to challenge our fundamental understanding of the cosmos. What began as a straightforward voyage now reveals deeper mysteries. Our journey has already established that space is expanding. Galaxies drift apart like dots on an inflating balloon. But the nature of this expansion presents us with our first major contradiction, one that has puzzled astronomers since the late 1990s. When scientists measured the expansion rate using different methods, they expected consistent results. Instead, they found a troubling discrepancy now known as the Hubble tension. Measurements based on the cosmic microwave background, the afterglow of the Big Bang, suggest one expansion rate. But when astronomers measure the actual recession speeds of nearby galaxies, they consistently get a higher value. This difference may seem small, but its implications are profound. It suggests either that our measurements contain systematic errors, or that something fundamental is missing from our understanding of cosmic evolution. Some theorists propose that a new form of radiation or an unknown particle might have influenced the early universe, altering its subsequent expansion. Others suggest modifications to Einstein's theory of gravity on cosmic scales. What does this mean for our endless journey? If we cannot precisely determine how quickly space expands, we cannot predict exactly what we would encounter in the distant future. The cosmic map becomes increasingly uncertain. Another contradiction emerges when we consider the universe's large-scale structure. According to our standard model, the cosmos should be roughly uniform when viewed at the largest scales, a principle called cosmic homogeneity. Yet recent galaxy surveys have revealed structures that seem impossibly large. The Hercules Corona Borealis Great Wall, for instance, spans approximately 10 billion light-years, a scale that challenges our understanding of how cosmic structure formed. These enormous galaxy superclusters shouldn't exist if our models are correct. They simply haven't had enough time to grow so large since the Big Bang, unless our understanding of gravity or dark matter is incomplete. As our journey continues into deeper space, we would eventually reach regions where these vast structures dominate the cosmic landscape. Their existence suggests hidden aspects of physics that remain beyond our current grasp. Perhaps the most profound contradiction concerns the universe's very beginning. Our standard model, the lambda-c/dm cosmology, describes cosmic evolution from a fraction of a second after the Big Bang until today with remarkable precision. But the Big Bang itself presents a singularity, a point where the mathematics breaks down. At time zero, all matter and energy were compressed into an infinitely dense point, a scenario that our physics cannot fully describe. This represents more than a gap in our understanding. It hints at a fundamental limitation in our ability to comprehend the ultimate nature of space and time. Our endless journey may be traversing a cosmos whose origin lies beyond complete explanation. When we travel far enough, we also confront the puzzle of dark matter. Astronomical observations reveal that galaxies and galaxy clusters contain far more mass than we can account for with visible matter alone. This invisible substance, dark matter, appears to make up about 27% of the universe's content. Yet, despite decades of searching, we haven't directly detected it. We only know of its existence through its gravitational effects. For a traveler journeying forever through space, dark matter would be a constant, unseen companion. You would pass through vast halos of it surrounding every galaxy, your path subtly influenced by its gravitational pull. But what is dark matter? Is it composed of undiscovered particles? Or does it represent a misunderstanding of how gravity works at cosmic scales? The answer would fundamentally change what our traveler experiences. Even more mysterious is dark energy, the force driving cosmic acceleration. Representing roughly 68% of the universe's energy content, it remains the most enigmatic component of our cosmological models. Current observations suggest dark energy behaves like a cosmological constant, a uniform energy density permeating all of space. But other models propose dynamic dark energy that changes over time, or modifications to Einstein's equations. For our endless journey, the nature of dark energy is crucial. If it remains constant, the universe will continue expanding forever, becoming increasingly empty. Galaxies would grow more isolated, eventually fading beyond any possibility of contact. But if dark energy changes over time, cosmic evolution could take unexpected turns. Some theories suggest it might eventually weaken, allowing gravity to pull everything back together in a big crunch. Others propose more exotic scenarios, like a big rip, where accelerating expansion eventually tears apart galaxies, stars, planets, and ultimately atoms themselves. Our traveler might witness the very fabric of reality dissolving. These competing models highlight a humbling truth. Despite extraordinary advances in cosmology, we still cannot say with certainty what would ultimately happen to someone traveling forever through space. Another contradiction emerges when we consider the universe's overall geometry. Einstein's general relativity allows for three possibilities: positive curvature, like a sphere; negative curvature, like a saddle; or flat, like a sheet. Current measurements from the cosmic microwave background suggest the universe is remarkably flat, so precisely flat that it strikes some physicists as suspicious. The probability of achieving such flatness by chance seems vanishingly small. This flatness problem hints at missing physics. One proposed solution, cosmic inflation, suggests the early universe underwent an incredibly rapid expansion that would naturally flatten any initial curvature. But inflation itself remains theoretical. While it elegantly solves several cosmological puzzles, direct evidence remains elusive. Our journey through space traverses terrain shaped by processes we still don't fully understand. Perhaps the most profound contradiction concerns the universe's apparent fine-tuning. Many physical constants seem calibrated with extraordinary precision to allow complex structures, including life, to exist. For instance, if the strength of the electromagnetic force differed by just a tiny percentage, atoms couldn't form stable structures. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. This apparent fine-tuning has led to various interpretations. Some see evidence of design. Others point to the anthropic principle. We observe these values precisely because they allow observers like us to exist. Still others propose a multiverse, where infinite universes exist with different physical constants. In this scenario, our endless journey might eventually reach the boundary of our universe and enter another realm entirely. The multiverse hypothesis represents a radical reconception of reality. Rather than a single cosmos, reality might encompass a vast landscape of universes, each with its own physical laws and constants. Some versions suggest these universes might occasionally collide, leaving detectable imprints on the cosmic microwave background. Our traveler might find subtle evidence of these cosmic neighbors in the distant radiation. String theory, a candidate for unifying physics, suggests the possibility of up to 10,500 different universes, each representing a different solution to the underlying mathematical equations. This number dwarfs even astronomical scales. For our endless journey, the multiverse concept raises the tantalizing possibility that continuing forever in one direction might eventually reach regions governed by different physical laws, though such transitions might not be survivable. As we ponder these contradictions, we must also consider the quantum nature of space itself. At the smallest scales, quantum mechanics suggest that space may not be smooth but granular. Various theories of quantum gravity propose minimum length scales, fundamental units below which distance loses meaning. If space is quantized, our journey would traverse countless discrete units rather than a continuous medium. This quantum structure might only become apparent at scales far smaller than atoms. But over an infinite journey, these quantum effects could accumulate, potentially altering the very nature of spatial displacement. These contradictions and mysteries remind us that our cosmic journey traverses not just physical space, but the boundaries of human understanding. As we venture further from Earth, we encounter phenomena that challenge our most fundamental concepts. Yet, rather than discouraging exploration, these contradictions drive scientific progress. Each anomaly, each unexpected observation points toward new physics, deeper understanding, and more complete models of reality. For our eternal traveler, the journey would be one of continual discovery, witnessing the cosmos not as a solved equation, but as an evolving mystery whose deepest secrets continue to unfold across endless light years. Chapter 6. Cosmic Fables, Separating Science from Speculation. As we contemplate our endless journey through space, we encounter not just scientific mysteries, but also persistent myths and misunderstandings. Some arise from genuine confusion, others from oversimplification, and some from the challenge of visualizing concepts that defy human intuition. Perhaps the most common misconception concerns the edge of the universe. Popular imagination often pictures the cosmos as a giant bubble with a definite boundary. Travel far enough, and you'd reach some cosmic wall. This image, though intuitively appealing, fundamentally misunderstands modern cosmology. The observable universe has a horizon, a limit to what we can see, but this isn't a physical boundary. It's merely the distance light has had time to travel since the Big Bang. Beyond this horizon, space almost certainly continues. Our traveler wouldn't encounter any wall, edge, or boundary. They would simply enter regions from which light hasn't yet had time to reach us. Another persistent myth involves the expansion of space itself. Many visualize this as galaxies flying apart through empty space, like shrapnel from an explosion. This mental image misrepresents what's actually happening. In reality, space itself stretches. Galaxies aren't moving through space so much as being carried along by space's expansion. The analogy of dots on an inflating balloon provides a better two-dimensional representation of this concept. For our eternal traveler, this distinction matters greatly. They aren't just moving through static space. They're navigating an actively expanding medium. The very fabric of their journey constantly stretches beneath them. A related misunderstanding concerns faster-than-light expansion. When astronomers say distant galaxies recede faster than light, they don't mean these galaxies break Einstein's cosmic speed limit. Rather, the intervening space expands so rapidly that the total separation rate exceeds light speed. This subtle distinction preserves special relativity while allowing for apparent superluminal recession. Our traveler could never catch up to the most distant galaxies, not because of conventional speed limitations, but because the space between keeps stretching too quickly. Social media has popularized various misconceptions about cosmic journeys. One viral claim suggests that traveling far enough would eventually show you the past due to light's finite speed, essentially watching Earth's history unfold in reverse. This fundamentally misunderstands how light propagation works. While looking back toward Earth would indeed show progressively older images as you travel outward, you would never catch up to light that left Earth before your journey began. Another common misconception involves black holes as potential shortcuts through space. Science fiction portrays these objects as cosmic tunnels or wormholes leading to distant regions or even other universes. Real black holes are quite different. Standard models describe them as regions where space becomes so curved that nothing, not even light, can escape their gravitational pull. They represent dead ends, not passages. While theoretical physics does explore wormhole concepts, these hypothetical structures differ fundamentally from black holes. Moreover, they would likely require exotic negative energy to remain stable, something we've never observed in nature. For our endless traveler, encountering a black hole would not provide a shortcut to distant regions. It would instead present an existential danger, a gravitational trap from which no conventional journey could continue. Many also misunderstand the Big Bang as an explosion that occurred at some point in empty space. This mental image suggests that traveling far enough would eventually reach the center of this cosmic detonation. In reality, the Big Bang wasn't an explosion in pre-existing space. It was the beginning of space itself, the initiation of expansion everywhere at once. There is no special central point where it all began. This means our traveler, journeying forever in one direction, would never find the origin point of the universe. The Big Bang happened everywhere, including the very spot where Earth formed billions of years later. Another persistent myth involves the universe's age versus its size. Many wonder how the universe can be 93 billion light-years across if it's only 13.8 billion years old. Wouldn't that require faster-than-light expansion? The answer lies again in understanding cosmic expansion properly. The most distant objects we observe today were much closer when they emitted the light now reaching us. Space has been stretching continuously during light's journey. Additionally, during the universe's first fraction of a second, a period called inflation may have expanded space faster than light speed. This rapid stretching, occurring before today's physical laws stabilized, helped establish our universe's enormous scale. Our endless traveler would navigate a cosmos shaped by this primordial inflation, a universe far larger than its age might naively suggest. The very notion of distance becomes complicated by space's dynamic nature. Some popular accounts suggest that traveling far enough might eventually bring you back to your starting point, like circumnavigating Earth. While theoretically possible in a closed universe with positive curvature, observations strongly suggest our cosmos doesn't have this geometry. Current data indicates the universe is remarkably flat, meaning parallel lines remain parallel even over cosmic distances. In such a universe, our traveler would never return to their starting point, regardless of how far they journeyed. Another misunderstood concept involves the multiverse idea. Often portrayed in science fiction as parallel realities one might physically travel between, the scientific multiverse hypothesis is far more nuanced and less accessible. Most serious multiverse theories don't suggest other universes exist elsewhere in our space. Rather, they propose entirely separate spacetimes, fundamentally disconnected from ours. Our eternal traveler couldn't simply journey to these other universes. Social media has also popularized misleading ideas about cosmic voids, the vast, relatively empty regions between galaxy superclusters. Some suggest these represent tiers in space or gateways to other dimensions. In reality, cosmic voids are simply regions with below-average matter density. They formed naturally as gravity pulled matter into filaments and clusters over billions of years, leaving these relatively empty regions between structures. Our traveler would find these voids largely unremarkable, just extended regions with fewer galaxies. While they might seem empty compared to cosmic filaments, they still contain scattered matter and the omnipresent dark energy. Perhaps the most persistent misconception involves cosmic topology, the overall connectedness of space. Many assume space must be simply connected, meaning any loop can be continuously shrunk to a point. But mathematics allows for more complex topologies. The universe might be multiply connected, like a three-dimensional torus or other exotic shape, while still appearing locally flat. This could create cosmic repeats where patterns of galaxies recur. For our endless traveler, a multiply connected universe would create a strange experience. After journeying far enough in one direction, they might encounter galaxy arrangements eerily similar to those they'd seen before. Scientists have searched for such periodic patterns in the cosmic microwave background, which would suggest a finite, multiply connected universe. So far, no convincing evidence has emerged, but certain anomalies keep the possibility alive. Another common misunderstanding involves the universe's expansion as a force pushing galaxies apart. In reality, expansion isn't a force at all. It's a feature of space-time itself. Galaxies don't feel any push driving them away from each other. This distinction matters for our traveler because it affects how they would experience vast distances. The expansion doesn't create any additional resistance or acceleration. It simply continuously increases the proper distance between objects. Many popular accounts also misrepresent the heat death of the universe, the theorized far future state of maximum entropy, often described as the end of everything. This scenario actually represents a transition to a different cosmic phase rather than cessation. In this state, our traveler would find a universe of scattered black holes, cold radiation, and perhaps occasional quantum fluctuations, different from today's cosmos, but still very much existing, albeit in a form inhospitable to conventional life. A particularly persistent myth suggests our universe might be someone else's simulation or computer program. While philosophically intriguing, this idea remains speculative and, importantly, outside testable science as currently formulated. For our traveler, whether the universe is real or simulated would make no practical difference to their journey. The laws of physics would operate consistently either way, and the vastness of space would remain equally challenging to navigate. When considering an endless journey, many mistakenly believe that technological limitations represent the primary obstacle. In reality, the fundamental physics of an expanding universe creates horizons that no technology, however advanced, could overcome. Our traveler, even with unlimited time and resources, would still find portions of the universe forever beyond reach. This isn't a failure of imagination or engineering. It's a consequence of the cosmos's basic structure. These misconceptions matter because they shape how we conceptualize space travel and cosmic structure. By clearing away these misunderstandings, we can better appreciate the true nature of our hypothetical endless journey. The reality of cosmic travel is both more limited and more wondrous than popular imagination suggests. While some doors remain forever closed due to physical law, others open onto vistas of complexity and beauty beyond anything we might have initially conceived. Chapter 7. The Cosmic Balance Sheet. Why our journey reveals. As our imaginary vessel continues its endless trajectory through space, we must now consider what truly matters about this thought experiment. Beyond the physics and astronomy, beyond the theories and contradictions, what does this journey tell us about ourselves and our place in the cosmos? The stakes of this question extend far beyond intellectual curiosity. How we understand the structure and fate of the universe shapes fundamental aspects of human civilization, from how we measure and navigate to how we conceptualize our collective future. Consider navigation first. Throughout human history, we've oriented ourselves using celestial objects. Ancient sailors used stars to cross vast oceans. Modern spacecraft use pulsars and distant quasars as fixed reference points. But in an expanding universe where everything is in motion, there are no truly fixed points. Our cosmic journey reveals that navigation itself becomes increasingly complicated as distances grow. Reference frames shift over time. For a civilization contemplating truly long-term projects, those spanning thousands or millions of years, this cosmic drift cannot be ignored. Star positions change. Galaxies move. The very framework of navigation evolves. This has practical implications even today. Our most precise astronomical measurements must account for cosmic expansion. GPS satellites, essential to modern navigation, require relativistic corrections to maintain accuracy. As our species develops more sophisticated technology, these cosmic considerations become increasingly important. Future interstellar missions will need to account for how the universe's structure affects extremely long-distance travel. Beyond navigation lies the question of measurement itself. How do we establish universal standards in an expanding cosmos? The meter was once defined as 1/10,000,000th of the distance from the North Pole to the equator. Today, we define it using the speed of light. The distance light travels in 1/299th, 792,458 of a second. But our endless journey reveals that even light doesn't provide a perfectly consistent measuring stick across cosmic scales and times. In regions of strong gravity, light paths bend. In expanding space, proper distances change over time. Even the cosmic microwave background radiation, often used as a universal reference frame, will eventually fade beyond detection. These measurement challenges reveal something profound. The universe doesn't provide absolute references. All measurement is ultimately relative, requiring us to carefully specify our reference frames and acknowledge their limitations. Perhaps most significant are the implications for telescope design and astronomical observation. As our journey extends into deep space, we would witness the changing appearance of the cosmos from different vantage points. From Earth, we see the universe from just one location at one moment in cosmic history. Our endless traveler would observe how galaxies appear from multiple angles, how cosmic structures reveal different facets when viewed from different positions. This perspective reminds us that our current astronomical picture remains limited by our vantage point. Future space telescopes, positioned at different locations in our solar system or beyond, might reveal aspects of the universe currently hidden from our view. The universe's vastness also imposes fundamental limits on observation. Light from beyond the cosmic horizon can never reach us. Information about those regions remains permanently inaccessible, not just practically, but in principle. This creates an epistemological boundary. a limit to what we can know about the cosmos. Our endless journey would eventually reach regions from which Earth can never be observed, because light from those locations hasn't had time to reach our planet. These observational horizons have profound implications for cosmology. They remind us that our models of the universe must always acknowledge incomplete information. The cosmos may be far larger than the portion we can observe. Timescales represent another crucial consideration. Our hypothetical journey through endless space would unfold across time spans that dwarf human history. Even traveling at near light speed, reaching another galaxy would require millions of years. This forces us to confront the mismatch between cosmic timescales and human ones. Our species has existed for roughly 300,000 years, less than a cosmic blink. Our written history spans only a few thousand years. Yet the processes shaping the universe operate across billions of years. Stars form and die. Galaxies collide and merge. The cosmos itself expands and evolves. Our endless journey would witness these changes directly. This temporal perspective matters for how we conceptualize humanity's future. If our species survives and continues to develop, we may eventually exist for millions or even billions of years, timescales comparable to cosmic processes. A truly long-lived civilization would need to adapt to a changing universe. Stars exhaust their fuel. Galaxies grow more isolated due to cosmic expansion. The cosmic microwave background fades. The night sky itself would slowly transform. Perhaps most poignantly, our journey reveals the possibility of cosmic loneliness. As the universe expands and accelerates, galaxies beyond our local group will eventually recede beyond reach, their light redshifted into invisibility. In the far future, trillions of years hence, observers would see only a single merged galaxy, the combination of our Milky Way and nearby galaxies bound by gravity. The rest of the universe would have disappeared beyond the cosmic horizon. This scenario, supported by current models of accelerating expansion, suggests that future civilizations might have no observational evidence for the broader cosmos. The rich universe we currently observe would become invisible. What a profound loss of perspective that would represent. Future astronomers might have no way to discover cosmic expansion, dark energy, or the Big Bang. The universe would appear static and limited rather than dynamic and vast. This possibility underscores the unique moment we currently occupy in cosmic history. We exist at a time when the evidence for cosmic origins and evolution remains observable, a temporary window of opportunity for understanding our universe. For any civilization undertaking an endless journey through space, this timing matters enormously. Setting out now while the broader cosmos remains visible provides navigational reference points and scientific understanding that may not be available in the distant future. Our thought experiment also reveals something profound about the relationship between physical travel and knowledge. Much of what we know about distant cosmic regions comes not from physical presence, but from analyzing the light that reaches us. In many ways, our telescopes and detectors already undertake the journey we're contemplating. They capture photons that have traveled across billions of light years, carrying information about distant regions we will never physically visit. This suggests that our species has already begun the endless journey in an informational sense. We extend our awareness across cosmic distances, even while our physical presence remains confined to Earth and its immediate vicinity. Modern physics even suggests that information may be more fundamental than physical objects, that the universe at its deepest level might be composed of information rather than matter. Our journey through space might ultimately be reconceptualized as a journey through information space. Perhaps most significantly, our endless voyage reveals the remarkable unlikelihood of our existence. The cosmos contains hundreds of billions of galaxies, each with hundreds of billions of stars. Yet here we are, on one small planet, contemplating it all. The vast emptiness our traveler would encounter The immense voids between galaxies, the even greater gaps between galaxy clusters, highlights how precious and rare complex structures like living beings may be in the cosmic context. This perspective doesn't diminish humanity, but rather elevates the significance of consciousness itself. In a universe that appears largely empty and inert, awareness represents something extraordinary. The cosmos evolved to contemplate itself. Our journey also reveals something about the nature of exploration itself. Throughout human history, we've been driven to discover what lies beyond the next horizon. This impulse has taken us across oceans, to mountaintops, and eventually into space. Yet our thought experiment suggests a profound truth. Exploration has no final destination. There is no endpoint to discovery, no moment when we can say, "Now we have seen everything." The journey itself is the constant. Perhaps most poignantly, our endless voyage through space reminds us of our temporal limitations. Individual humans live brief lives compared to cosmic timescales. No single person would experience much of the journey we've contemplated. This highlights the intergenerational nature of human knowledge. Scientific understanding accumulates across centuries as each generation builds upon the discoveries of those who came before. Our cosmic understanding represents a collective journey through time. As we prepare to conclude this segment of our exploration, we stand at another threshold. We've examined what our endless journey reveals about navigation, measurement, observation, and time, the practical stakes of understanding cosmic structure. But deeper questions await us. If physical travel across cosmic distances remains practically impossible, what other ways might consciousness expand into the cosmos? Could technology eventually enable forms of presence that transcend physical limitations? And what of the universe's ultimate fate? Current evidence suggests accelerating expansion, leading to a cold, dark future where most matter is isolated in separate bubbles of spacetime. But is this conclusion certain, or might new discoveries reveal alternative possibilities? These questions await us in the final segment of our journey, where we'll explore the furthest reaches of scientific understanding and confront the ultimate mysteries that may forever lie beyond human comprehension. But already our voyage has revealed something profound. The universe doesn't exist separate from our understanding of it. The cosmos and consciousness have evolved together, each giving meaning to the other across the vast emptiness of space. Chapter 8. Cosmic Pathways. The leading theories as our journey through infinite space continues. We must now examine the most compelling scientific theories that attempt to answer our central question: what truly happens if you travel forever through space? Modern cosmology offers several sophisticated models, each with its own implications. The first and currently most supported theory is the eternal expansion model. Based on observations of accelerating cosmic expansion, this framework suggests that our endless traveler would witness the universe becoming increasingly sparse and isolated. In this scenario, galaxies outside our local gravitationally bound group would gradually recede beyond our cosmic horizon. The space between galaxy clusters would stretch faster than light could cross it, creating permanently unreachable regions. Our traveler would eventually find themselves in an island of matter, the merged remains of our local group of galaxies, surrounded by an ever emptier void. The once crowded cosmic neighborhood would transform into a vast, dark emptiness. Given billions or trillions of years, even the stars within this island would exhaust their fuel. What remained would be stellar remnants, white dwarfs, neutron stars, and black holes, slowly radiating away their remaining energy into the expanding void. After unimaginable time spans, even these objects would decay. Black holes would evaporate through Hawking radiation. Protons might decay into lighter particles. All organized structures would eventually dissolve into a thin soup of elementary particles and radiation. This, heat death, represents the ultimate fate in the eternal expansion model, a universe of maximum entropy where no meaningful structures or energy gradients exist. Our traveler would witness the universe's transition from complex organization to featureless uniformity. What makes this theory compelling is its consistency with current observations. The accelerating expansion, discovered in 1998 through studies of distant supernova, aligns perfectly with this model. It also fits neatly within Einstein's general relativity. However, this model has weaknesses. It assumes dark energy will remain constant indefinitely, something we cannot yet confirm. If dark energy's properties change over time, the universe's fate could differ dramatically. The second major contender is the Big Bounce theory. This model suggests that the universe's expansion will eventually reverse, leading to a big crunch where all matter reconverges, potentially triggering another Big Bang. For our cosmic traveler, this would mean eventually finding themselves pushed backward as space itself begins contracting. The outward journey would reverse, with galaxies moving closer together rather than farther apart. As contraction accelerated, they would witness the universe growing denser and hotter. Galaxy clusters would merge. Stars would be torn apart by tidal forces. Eventually, even fundamental particles would be compressed into an ultra-dense state. This scenario offers a cyclical view of cosmos: expansion followed by contraction, followed by rebirth. Rather than ending in featureless emptiness, the universe rejuvenates itself through periodic crunches and expansions. What makes this theory appealing is its elegant symmetry and its solution to the beginning problem. Rather than requiring a singular creation event, it suggests the universe has always existed in cycles of expansion and contraction. However, current observations of accelerating expansion strongly contradict this model. For a big bounce to occur, gravity would need to eventually overcome dark energy's expansive force, something that appears increasingly unlikely based on present data. Some variations of Big Bounce theory incorporate modified gravity or quantum effects that might eventually halt expansion. These remain speculative, but represent active areas of theoretical research that could potentially revive this elegant model. A third intriguing possibility comes from string theory and quantum gravity, the multiverse membrane model. This suggests our universe is just one of many membrane-like structures, floating in a higher dimensional space. In this scenario, our traveler journeying forever in one direction might eventually encounter boundary phenomena, subtle changes in physical constants or forces as they approach the edge of our universal membrane. This could manifest as gradual shifts in how light propagates, how gravity behaves, or how particles interact. The traveler wouldn't hit a wall, but might notice increasingly foreign physics as they ventured into boundary regions. In the most extreme version of this theory, our Voyager might even transition into another universe entirely, a different membrane with its own physical laws and constants. Whether consciousness could survive such a transition remains highly speculative. What makes this theory compelling is its potential to explain certain cosmological anomalies and its foundation in cutting-edge theoretical physics. It provides a natural framework for understanding why our universe has the properties it does. However, the membrane multiverse remains largely theoretical. While mathematically consistent, it lacks direct observational evidence. Critics argue it pushes explanation beyond the testable realm, potentially straying from scientific methodology into metaphysics. Each of these theories presents a different fate for our eternal traveler. In the eternal expansion model, they witness gradual emptiness and dissolution. In the Big Bounce, they experience cosmic rebirth. In the multiverse membrane, they might transcend our universe entirely. Importantly, these are not merely competing guesses. Each theory makes specific predictions about cosmic evolution that can be tested through observation. As our measuring tools become more sophisticated, we may eventually determine which most accurately describes our reality. For instance, precise measurements of dark energy's properties over time could reveal whether it truly remains constant, supporting eternal expansion, or changes in ways that might eventually permit contraction, supporting big bounce. Similarly, certain patterns in the cosmic microwave background radiation might reveal the bruises of collisions with other universe membranes, providing evidence for the multiverse hypothesis. Scientists actively search for such signatures. What's particularly fascinating is how these competing theories reflect different philosophical approaches to cosmology. Eternal expansion embraces the universe's impermanence. Big bounce suggests cosmic renewal. Multiverse membrane points to realities beyond our own. For our traveler journeying forever, these philosophical distinctions would eventually manifest as tangible experiences, whether witnessing eternal dissolution, cosmic rebirth, or transition between different universal domains. Beyond these mainstream theories lie more speculative possibilities. Some physicists suggest the universe might be holographic, a three-dimensional projection of information encoded on a two-dimensional boundary. In such a model, our traveler moving forward forever would actually be traversing information patterns rather than conventional space. At extreme distances, they might encounter artifacts of this encoding, glitches in the cosmic hologram. Another fascinating possibility comes from quantum mechanics. Some interpretations suggest that space itself isn't fundamental, but emerges from underlying quantum entanglement relationships. Space isn't a thing, it's a pattern of connections. In this framework, our endless journey might eventually reveal space's granular, emergent nature. At extreme distances, the traveler might experience quantum fluctuations in spacetime itself, evidence that smooth, continuous space is merely an approximation. Each of these theories attempts to reconcile what we observe with what we calculate, what we measure with what we theorize. They represent humanity's best efforts to comprehend the ultimate structure and fate of our cosmic home. As we continue our journey, remember that science embraces uncertainty. These models represent our current understanding, subject to revision as new evidence emerges. The map is not the territory. Our theories approximate a reality far richer than our models. What's remarkable is how far these theories have come from early human cosmologies. We've moved from flat Earth supported by turtles to sophisticated mathematical models of expanding spacetime and membrane. Multiverses, an extraordinary evolution in understanding. For our endless traveler, the journey itself transcends any particular cosmological model. It represents the fundamental human drive to explore, to question, to push beyond known horizons, both physical and intellectual. Chapter 9. The New Cosmic Explorers, Instruments on the Edge. While our hypothetical vessel journeys through endless space, real scientific instruments are extending humanity's vision further into the cosmos than ever before. These remarkable tools don't physically travel vast distances, but they capture information from the furthest reaches of the observable universe. The James Webb Space Telescope, launched in late 2021, represents a quantum leap in our ability to peer into cosmic history. With its massive 6.5-meter primary mirror and sensitivity to infrared wavelengths, it can detect light from the universe's earliest structures. This capability transforms our understanding of what an endless journey would encounter. Webb has already revealed galaxies forming just a few 100 million years after the Big Bang, cosmic structures, taking shape when the universe was less than 3% of its current age. These observations challenge previous models of galaxy formation. Massive, surprisingly mature galaxies appear much earlier than expected. For our eternal traveler, this suggests the early universe was more structured and complex than previously thought. Webb's infrared capabilities also allow it to peer through cosmic dust clouds that obscure visible light. This reveals star-forming regions in unprecedented detail, showing how matter coalesces into new stellar systems, waypoints on our endless journey. Perhaps most significantly, Webb can analyze the atmospheric composition of exoplanets, worlds orbiting distant stars. As our traveler journeys forever, they would encounter countless planetary systems. Webb gives us our first glimpse of what these worlds might be like. On Earth, equally revolutionary instruments expand our understanding in complementary ways. The Extremely Large Telescope, ELT, under construction in Chile, will feature a primary mirror 39 meters in diameter, nearly 6 times larger than Webb's. This enormous light-gathering capacity will allow astronomers to study individual stars and galaxies beyond our local group, something previously impossible. Our endless traveler could witness stellar populations throughout a much larger volume of the cosmos. The ELT will also search for direct evidence of cosmic acceleration by measuring subtle changes in the expansion rate over time. This could determine whether dark energy remains constant or changes, a crucial factor in predicting what our traveler would ultimately encounter. Perhaps most exciting are the new messengers bringing information from the cosmos, particles and waves beyond conventional light. Gravitational wave observatories like LIGO and Virgo have opened an entirely new window on the universe. These instruments detect ripples in space-time itself, created when massive objects like black holes collide. Since 2015, dozens of such events have been observed, revealing a population of black holes with unexpected properties. For our endless journey, gravitational waves reveal the dynamic nature of space itself. As our traveler ventures forever outward, they would pass through countless invisible ripples in space-time, echoes of violent cosmic collisions throughout the universe. Unlike light, gravitational waves pass through matter virtually undisturbed. They carry information from regions that remain optically obscure, revealing processes hidden from traditional telescopes. They provide a more complete picture of what our traveler would encounter. Equally revolutionary are neutrino observatories buried deep underground or in Antarctic ice. These elusive particles interact so weakly with matter that they pass through entire planets almost unimpeded, carrying information from the cosmos's most extreme environments. Neutrino detectors have already captured particles from supernova explosions and active galactic nuclei. For our cosmic traveler, neutrinos reveal the universe's most energetic processes, stellar deaths, matter falling into supermassive black holes, and other cosmic cataclysms. These new messengers, gravitational waves and neutrinos, complement traditional electromagnetic astronomy to create a multi-messenger approach. Together, they reveal a more complete picture of cosmic events than any single method could provide. This multi-messenger approach has already yielded extraordinary discoveries. In 2017, the merger of 2 neutron stars was observed simultaneously in gravitational waves and across the electromagnetic spectrum, confirming these objects as sources of heavy elements like gold and platinum. Our endless traveler would encounter the products of these neutron star mergers throughout their journey. Precious metals incorporated into new generations of stars and planets, cosmic alchemy witnessed through our new astronomical tools. Perhaps most tantalizing are the cosmic mysteries these new instruments have revealed. The more we observe, the more we discover phenomena that challenge existing theories, hints that our understanding remains incomplete. Fast radio bursts, FRBs, millisecond-long flashes of radio, energy from distant galaxies, were unknown before 2007. Now hundreds have been detected, but their exact cause remains debated. Our traveler might pass through countless sources of these enigmatic signals. Similarly, astronomers have detected enormous, diffuse structures like the Boat's Void, a nearly spherical region nearly 330 million light-years across, containing few galaxies. Our traveler would cross these cosmic deserts, their origins and nature still not fully understood. The South Atlantic Anomaly, a region where Earth's magnetic field is significantly weaker, reminds us that even well-established fields contain anomalies and exceptions. Cosmic magnetism, largely invisible to our eyes, would influence our traveler throughout their endless journey. New research even suggests modifications to our understanding of cosmic expansion itself. Some analyses indicate the universe may be lopsided, expanding slightly faster in one direction than others. If confirmed, this would fundamentally change our cosmic map. For our traveler, this cosmic anisotropy would create subtle but cumulative effects over vast distances. The universe might appear increasingly different depending on which direction they journeyed, a profound asymmetry in the cosmic fabric. These observational puzzles generate new theoretical frameworks. Some physicists propose modified gravity models to explain cosmic acceleration without dark energy. Others suggest interactions between dark energy and dark matter that evolve over cosmic history. Each new model makes specific predictions about what our endless traveler would experience in the distant future. Would they witness dark energy strengthening, weakening, or oscillating? Would gravity behave differently at extreme distances or after trillion-year timescales? The theoretical landscape continues expanding with concepts like bubble universes, the idea that our observable cosmos might be one expanding bubble in a larger multiversal sea, with other bubbles occasionally colliding with ours. For our cosmic traveler, such collisions might manifest as subtle discontinuities in the laws of physics, regions where constants like the speed of light or strength of electromagnetism differ slightly from their values elsewhere. Even more speculative frameworks propose that information, not matter or energy, represents reality's fundamental substrate. In such models, our traveler's journey through space would ultimately be a traversal through information configurations. This perspective aligns with holographic principle theories, suggesting our three-dimensional reality emerges from information encoded on a two-dimensional boundary. Our traveler might eventually encounter manifestations of this deeper structure underlying apparent spacetime. Each new instrument and observation either strengthens existing models or challenges them, refining our cosmic understanding. This iterative process doesn't guarantee we'll ever have a complete picture, but ensures our models continuously improve. For our endless traveler, this expanding knowledge base enriches their journey. What might have seemed like featureless voids to ancient observers reveal themselves as regions teeming with dark matter, neutrino streams, and gravitational waves. What might have appeared as simple points of light resolve into complex stellar systems with planets, moons, asteroids, and comets, each with unique compositions and histories, each a potential waypoint on an infinite voyage. The cosmic web itself, the large-scale structure of galaxy superclusters connected by filaments, emerges more clearly with each new survey. Our traveler would navigate this intricate pattern of matter distribution stretched across billions of light years. Perhaps most profoundly, these new instruments reveal the universe as dynamic rather than static. Galaxies collide and merge. Stars explode and form. Black holes evolve. Our traveler would witness a cosmos in constant transformation. This dynamic quality extends to space itself, stretching, warping, rippling with gravitational waves. Even the empty regions between galaxies contain diffuse gas, magnetic fields, and the omnipresent influence of dark energy and dark matter. As our instruments continue to improve with larger telescopes, more sensitive detectors, and entirely new observation methods, our map of what an eternal journey would encounter becomes increasingly detailed and accurate. Yet humility remains essential. Each answered question typically generates several new ones. The horizon of our ignorance expands alongside our knowledge. Our traveler would likely encounter phenomena we haven't yet imagined. Chapter 10. The Infinite Horizon. What truly awaits. We've traveled far in our exploration, examining theories and evidence, instruments and observations. Now we must confront our central question directly. What truly happens if you keep traveling through space forever? The answer emerges from synthesizing everything we've learned. Our journey reveals a profound truth. The fate of an endless traveler depends entirely on when they begin their voyage. The universe isn't static, it evolves. What lies ahead for our cosmic explorer depends crucially on their starting point in cosmic history. Had they begun billions of years ago, shortly after the Big Bang, they would have witnessed a dramatically different cosmic landscape, denser, hotter, more uniform. Their path would have carried them through the formation of the first stars and galaxies. Had they begun their journey trillions of years in the future, they would encounter an increasingly empty cosmos, most galaxies having receded beyond the cosmic horizon, leaving only the remnants of our local group visible. This temporal dependence reveals something fundamental. Our question can't be answered without specifying when the journey begins. The universe itself changes too dramatically over cosmic timescales for any single, timeless answer to suffice. For a journey beginning in our present cosmic epoch, about 13.8 billion years after the Big Bang, the evidence points toward a specific sequence of encounters and transitions that our traveler would experience. First, they would cross our solar system, requiring years even at substantial fractions of light speed. Then would come the interstellar medium, the relatively empty space between stars, filled with diffuse gas and cosmic dust. Next would come neighboring stars and their planetary systems, the closest being Proxima Centauri, about 4.2 light-years away. Different stellar systems would reveal incredible diversity: red dwarfs, binary stars, massive blue giants. Continuing outward, our traveler would eventually reach the edge of our galaxy after about 50,000 light-years, depending on their direction. They would then enter intergalactic space, the vast void between galactic islands. This intergalactic medium, once thought empty, actually contains diffuse gas at temperatures of millions of degrees, occasional rogue stars ejected from galaxies, and the omnipresent dark matter detectable only through its gravitational effects. After millions of light years, they would encounter another galaxy, perhaps Andromeda if traveling in that direction. They would witness an entirely different collection of stars, potentially with different chemical compositions, reflecting distinct evolutionary histories. Continuing their journey, they would eventually reach the edge of our local group of galaxies after a few million light-years. Beyond lies the local void, an enormous region of relatively empty space surrounding our galactic neighborhood. After tens of millions of light-years, they would reach other galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity. Each would demonstrate different evolutionary stages, shapes, and star formation rates. Between these clusters runs the cosmic web, filaments of galaxies stretching across hundreds of millions of light-years, with enormous voids between them. Our traveler would cross these structures, witnessing the universe's largest-scale architecture. But here is where the journey becomes truly remarkable. Due to cosmic expansion, the space between galaxy clusters continuously stretches. The further apart objects are, the faster they recede from each other. At distances of billions of light-years, this expansion exceeds the speed of light. Not because objects move through space faster than light, which relativity forbids, but because the intervening space itself expands rapidly enough to separate them at superluminal rates. This creates a cosmic horizon, a boundary beyond which objects recede faster than their light can travel toward us. Our traveler, even moving at nearly light speed, could never reach galaxies beyond this horizon. Moreover, this horizon isn't fixed. As cosmic expansion accelerates due to dark energy, galaxies currently visible will eventually cross this boundary, disappearing forever from potential contact. The observable universe continuously shrinks in terms of what remains accessible. This leads to our first major revelation. An endless journey through space cannot access the entire universe. Regardless of how long our traveler journeys, whole regions remain forever beyond reach due to cosmic expansion. What's accessible to our traveler forms an eventually reachable volume, the portion of the cosmos they could theoretically visit given infinite time. Based on current measurements of dark energy, This volume contains approximately 100 billion galaxies. Beyond this lies a much larger cosmos, perhaps infinitely larger, that remains forever inaccessible. Our traveler could journey eternally without ever reaching these regions. Physical limitations, not technological ones, create this boundary. Within the reachable volume, our traveler would encounter the full diversity of cosmic structures. Galaxies ranging from giant ellipticals with trillions of stars to dwarf irregulars with just a few million vast clouds of gas and enormous black holes. They would witness galaxies in different evolutionary stages, some actively forming stars, others largely dormant. They would see galaxies colliding and merging, creating spectacular starburst events and triggering the formation of new stars from compressed gas. They would encounter exotic objects rarely seen in our cosmic neighborhood, quasars powered by supermassive black holes, actively consuming surrounding matter, magnetars with magnetic fields trillions of times stronger than Earth's, and perhaps stranger phenomena yet undiscovered. But here we encounter our second major revelation. The journey would never reach a stable endpoint. The universe constantly evolves. Stars exhaust their fuel and die. Galaxies merge. Space expands. Nothing remains static over cosmic timescales. For the first few trillion years, our traveler would witness a universe not dramatically different from today's. Galaxies would continue forming stars, though at declining rates as gas supplies diminish. Galactic collisions would slowly reduce the number of separate galaxies. But over longer timescales, quadrillions or quintillions of years, more dramatic changes emerge. Stars exhaust their hydrogen fuel. The smallest red dwarfs, most common in the universe, would be the last to fade after trillions of years. Eventually, only stellar remnants would remain: white dwarfs, neutron stars, and black holes. The once luminous galaxies would become dark collections of dead stars, occasionally punctuated by brief flashes when these remnants collide. Over even longer timescales, proton decay, if it occurs, would gradually erode matter itself. Black holes would slowly evaporate through Hawking radiation. The universe would transition toward an ever more diffuse, cold, and homogeneous state. This progression reveals our third major finding. An endless journey through space is simultaneously a journey through cosmic history. The traveler wouldn't just visit different locations, but different epochs in the universe's evolution. What begins as a spatial journey becomes temporal as well. Moving far enough in space means witnessing the far future of cosmic evolution, regions where stellar life cycles have progressed further, where galaxies have evolved differently. But perhaps the most profound revelation comes from considering the traveler themselves. Any consciousness undertaking such a journey would inevitably evolve and transform. The traveler, at journey's start, would differ fundamentally from their future self. This highlights an essential paradox. The endless journey transforms both the explorer and the explored. The universe changes as it evolves. The traveler changes through their experiences. Neither remains static across cosmic timescales. In this light, our question reveals a deeper truth. There is no fixed answer because there is no fixed universe and no fixed traveler. Both are dynamic, evolving entities whose interaction creates a unique cosmic narrative. So what truly happens if you keep traveling through space forever? You encounter a universe of increasing emptiness and isolation as cosmic expansion carries most matter beyond reach. You witness the gradual transition from our vibrant cosmos to one of diffuse radiation. But you also potentially discover phenomena currently unknown, structures and processes beyond our current cosmological models. You map the boundaries of the physically accessible universe. And through this endless exploration, you evolve alongside the cosmos you traverse. The journey has no destination, no endpoint, no final discovery that resolves all questions. Instead, it offers continuous revelation, an endless sequence of horizons, each revealing new vistas once crossed. none representing a final answer or ultimate truth. This may seem unsatisfying to our human desire for closure and certainty, but it perfectly reflects the universe as science currently understands it. Not a finished product, but an ongoing process. Not a static backdrop, but a dynamic, evolving system. In this sense, the endless journey through space becomes the perfect metaphor for scientific inquiry itself, a process without end, where each answer generates new questions, where exploration continues without the expectation of reaching final, absolute truth. Perhaps this is the deepest answer to our question. What happens when you travel forever through space is that you participate directly in the fundamental nature of reality. Continuous transformation without end. Exploration without final destination. As we conclude our cosmic voyage, we find ourselves back where we began, here on Earth, gazing upward at the stars. Yet something has changed. The perspective gained from our imaginary journey alters how we perceive our place in the cosmos. Though we haven't physically traveled beyond our planet, our minds have traversed billions of light years. We've contemplated endless journeys through expanding space, witnessed the birth and death of stars, and considered the ultimate fate of all matter and energy. This mental voyage reveals something profound. The greatest distances we can travel are often within. Our consciousness can span cosmic horizons that our bodies never will. Through understanding, we transcend our physical limitations. The universe exists both around and within us. The atoms in our bodies were forged in stellar furnaces billions of years ago. We are, in a very real sense, the universe becoming aware of itself, stardust, contemplating stars. Our question about endless travel through space ultimately leads us to the meaning of the journey itself. Perhaps it's not about reaching a destination, but about the continuous process of discovery, the perpetual expansion of understanding. In this light, each of us already undertakes an endless journey, not through physical space, but through the landscape of knowledge and awareness. Each new understanding becomes a stepping stone to further questions, further horizons. The cosmos offers no final answers, no ultimate destinations, only continuous unfolding. In embracing this open-ended exploration, we align ourselves with the fundamental nature of the universe itself, always evolving, always becoming. As you drift towards sleep tonight, carry this cosmic perspective with you. You are a conscious element of an immense, mysterious universe, one capable of contemplating its own existence. Join us again for another journey through the wonders of space and time.